Our paper looked at how to learn symbolic action definitions from unlabelled image pairs. This work was done as part of my PhD at Ghent University, which was supervised by Pieter Simoens. I've since moved to the University of Lincoln. During this presentation, I will use the example of the Towers HANOI domain, in which the aim is to rearrange the disk from a start configuration to get to an end configuration. Disks can only be placed on larger disks. The actions of this domain can be defined in PDDL, which stands for Planning Domain Definition Language. These actions contain a set of parameters, preconditions, and effects. Actions can be provided to task plans along with an initial and goal state in order to generate a task plan. Action definitions are usually manually written, which can be a time-consuming and error-prone process. Our paper looked at how do we translate pairs of images showing the state before and after an action has taken place into an action definition. We assume that no objects overlap and that actions are discrete. Our work starts by discovering the locations that change value and what values those locations can have. This information is used to generate a PDDL-defined state of each of the images. This enables grounded actions and static atoms to be created, which are then finally transformed into action definitions. So the aim of our first step is to extract the locations that change value. For the Towers of HANOI domain, that is these 12 locations. This is performed by finding the regions of the images that change. In the first transition, this is the region we are looking for. In the second transition, we find this region. The overlapping changed image areas are then discovered. This results in a long list of areas which are sorted from smallest to largest, and then iterated over to discover the largest non-overlapping areas to be added to our set of location objects. Objects are given an ID to enable them to be transformed to and from PDDL. The value that these locations can be set to are then discovered. This is performed by looking at which of the locations change value within a transition and extracting just the pixels that changed. Once we know what objects the images contain, the images are transformed into states. In this example, image object 12 is in location 0, image object 13 in location 1, and so on. If a location does not contain an object, then we create a clear atom. These states are used to turn each of the transitions into an action. Known preconditions are the objects that change value and the effects of their resulting value. Possible preconditions are all the remaining atoms shared by the two states. To prevent invalid actions from being generated from the resulting action definitions, we add static atoms to the preconditions of the grounded actions. Linked locations are locations that can change value simultaneously. Locations can also depend on the value of other locations. So for instance, for location 4 to be able to change value, location 5 must be clear. Image objects can also depend on the value of different objects. In the case of the Towers of HANOI domain, the image object dependencies prevent disks from being placed on smaller disks. Once we've created our set of grounded actions, we then transform that set of actions into a set of PDDL-defined action definitions. This results in a set of difficult to read action definitions. So for the Towers of HANOI domain, 6 action definitions are created. In this example here, image object, a grounding of image of the parameter 6 is the image object that changes value from some location defined by parameter 1 to a location of parameter 4. As well as performing experiments with the tiles of HANOI domain, we also performed experiments with some puzzle domains containing digital numbers, a mandrel and a spider. We also looked at the lights out domain. For our experiments, initial and goal states were generated from 2 images and passed to the fast downward task planner. The planned actions were then transformed back into images. The longest time it took for FD to generate a plan using our learned action definitions was 0.71 seconds. On average, 0.06 seconds were used. Our paper also presents experiments using missing transitions. Our method extracted objects from images in order to generate a state for each image. This knowledge was then used to translate the pairs of images into actions. Static items are inserted to prevent invalid actions from being generated, and finally actions were transformed into action definitions. In future work, we could explore more complex domains and images. However, the scalability of our approach will need to be improved. We want to remove some of the assumptions we make. For instance, we want to enable occluded objects to be handled. The understandability of the produced action definitions could also be improved.